It is section 4.3, numerical integration. Numerical integration can be performed by first approximating the function f by an interpolating polynomial and then integrating the polynomial over the prescribed interval. It is simple, right? Let x0, x1, and xn be distinct points in the interval AB, then the interpolating polynomial in Lagrange form can be written as in this equation. We integrate the polynomial as an approximation of the integral of f, and by using the equation we can write the integral in this equation. Once we can get the value, the integral of ln I, and we name it ai, then this can be written as a weighted sum of function values. Of course, ai can be obtained quite easily because this ln I is the ith cardinal function, nth order polynomial, so the integral can be obtained easily. This formula is called a Newton-Cotes formula when the knots are equally spaced. Let's consider the simplest case. If we set n equal 1, then the knots are here x0 is A and x1 is B. For this small interval, we can get the linear interpolation and here error, and its integration can be written in this way. So here integral from x0 to x1 of f is same as this is two terms, and then now integral of the interpolation error. We can evaluate this one easily. Here a0 is integral of L10. Now L10 is given explicitly in this way, so that we can get that. And for L1, we can get the same result. Pictorially, we can explain it quite easily. Okay, we are dealing with now here x0 to x1, and here ln 0, the cardinal function must be given in this way. There's 1 here, and the value is 0. There is L10. So the integral of L10 must be the area of this triangle. The bottom length is x1 minus x0, and height is 1, and multiply half, so that we can get this formula. And for L11, that is given here, start from 0 and becomes 1 here, so that again for this triangle the area must be the same, so we can get these values. And for the error, now this is non-negative and this portion is non-positive, so that this is non-positive. It's not changing sign. So by using weighted mean value theorem on integral, we can here move this one by using its average value, and the constant can go out, and here we have integral from x0 to x1 and this part, and we can get the exact value for the integral, so we reach at this one. Here we summarize our the derivation in this definition. the corresponding quadrature formula is here integral from x0 to x1 f of x dx is the same as, now here from x0 x1 the distance is h. We assume here from x0 x1 the distance is h, then that is now minus f double prime at some point over 12 and h cubed. That is exactly the error term. For this interval, that will be used as the numerical integration, and this is error. So that now that is called the Trapezoid rule, because that linear interpolation is eventually making so that the integration will make the area of trapezoid. Okay, so that is trapezoid rule having error in third order. Now we'll see here f is given in this way, and here now from 0 to 1 we'll try to get integration. The true value is from this one quarter and from this one 2, so that 2 and quarter 2.25, and then integration of this curve is 0, so that the exact value is 2.25. Now with one interval, that is the area of this trapezoid, the now what is the value? Okay, here the value integral is 2.5, so it is larger than exact value. And once we try to use two subintervals, so that there's x0 and x1, and we make one here trapezoid, and again from here to there we make another trapezoid, and area that's summed, then the integral is 2.3125. It is better. So if we try to use many subintervals, then the approximation is better. So here, this elementary trapezoid rule can be applied for each subinterval. Then for each subinterval, we have this amount of error, and now so that total error can be addition of that. However, if you are choosing more points, then the approximation will be better. That is the idea of the composite trapezoid rule. Now, for given interval, we make a partition from x0 to xn, so there are n sub-intervals. Then, from a to b integral of f is the same as for each subinterval. Now we integrate the function and sum over the subinterval. That is the same. Now for each one, that one, now we try to use the trapezoid rule, so that is now approximation. So it's a sum of these terms, and half hi and left h value and right h value of the subinterval. Okay, that is composite trapezoid rule. Okay, so that once here we choose uniform spacing, so that hi is all the way the same as h, as in this formula. xi is a plus I times h. H is now b minus a over n. Then the composite trapezoid rule can take this form. Now here, integral from a to b f of x dx is same as h times. Now for the beginning point is half contribution and end point half contribution, and interior points is one contribution. We'll see here. We'll try to figure out the formula by using the picture here. Now from a to b, now that is a, that's x0, b is now xn, now x1, x2, x3, x4, now, and so on. So the last one is xn. Now for each subinterval, here left value is half contribution and right value is from here to there, again, half contribution. And for this subinterval, again, left value, half contribution, right edge value, half contribution, and so on. We continue this way. Then for interior points, is half from left-hand side, half from right side, so that each interior point has one contribution. And for edge values, we have half contribution. That is the formula for the composite trapezoid rule. And the error can be here accumulated. From each subinterval, we have this amount of error. Look at here, the formula here. So for each subinterval, we have this amount of error, minus h cubed over 12 f double prime at some point. Okay. Now, so that the total error is the addition of those local errors. So that I is 1 to n, we have this error. Now, assuming this is continuous, then we can put this one out of the summation by using its average value. And now this is a constant, n times of addition, we can get this one. Now, h is b minus a over n, so that n is same as b minus a over h. By using this term, replacing n with this term, we can reach at this error. So the composite error is order h squared, and locally h cubed, but that will be added over the whole domain, so that it becomes h squared. Okay. Now here we have the same function. We already know that error is the exact value is 2.25. Now along with 8 subinterval, we have value here 2.25, 39, 0.250, so that this portion is the error. Now once we define so that we have 16 subintervals, then now the values given here, so that this portion is the error. As you can see here, the error over there is quarter of the error in this case. So that by halving and by choosing twice more points and having the h size, we can get quarter error. Okay, so it is error is order h squared, right? Okay, that's the end of part 1. We'll consider the Simpson's rule and Simpson's 3/8 rule in the second part. Thank you.